Okay, so thank you so much for joining us this evening. We've got um, Ed Gerber and Hamid from Datawave. Hand it over to you guys.
Okay, thanks for the opportunity to speak. And can you see my cursor if I do that? Does that come through? Great. Yep. So today, this would be part one of a two-part talk. We're talking about the graph versus host problem, which is the idea that we're going to train data-driven parameterizations using data or high-resolution models really that are constrained by data. And then we have to graph these into climate models. And of course, we want our patient to survive, right? We need stability, but we want to move beyond that. We want the patient to thrive. So how do we make sure that works? And that's going to involve a lot of calibration. So that's what we wanted to talk about today. Hopefully emphasizing some things that will be common among many of the data-driven parameters, the different activities going on in Vestry. So my talk will be more introduction. I'm going to be highlighting work by Ofer Shamir. This is a paper that was just out in the QJ with a lot of people at Collaborators, mostly at NYU, but also Stephen Hardiman at the Met Office. And then Hamid will do the second half. We'll be getting more into the details of how do we do calibration and some ideas of using offline online learning. Again, thanks to the Schmidt Sciences and also the NSF that helps sponsor this research. So I'll start off with, why do we care about gravity waves, or what are gravity waves? Not gravitational waves, nothing about the cosmos here, but just buoyancy waves. These are a beautiful picture of the South Sandwich Islands. That's where they are right here. So here's South America and then the Antarctic Peninsula. So this is a beautiful place for creating gravity waves because you have a huge, strong jet coming along over the Drake Passage. And then it hits these small obstacles, these really tiny islands. They're just like kilometer scale islands. They're roughly 100 kilometer scale apart. And what we're looking at here is we're looking at clouds. So what's happening is these waves are going up and you have uplift and descent within that waveform. During uplift, you have expansion that builds cloud. When you have down, you're compressing, warming up, re-evaporating that fluid. So we can see it from here. And you can say, well, why do we care about them? They are associated with clear air turbulence, another story. But for here, it's really that they're moving momentum, right? This is, they have these strong winds shooting across the ocean. They hit these islands, and then that's going to have the land is going to have a drag on the flow. If it was just that, well, then you'd slow down the boundary layer. But when you produce these gravity waves, that drag on the flow will be propagate up to where the wave breaks. Okay, so it's a mechanism for moving momentum into the free troposphere. And that's why we need to do it, right? They shape really the large scale circulation. It gets shaped by this momentum transport. I'm sorry if this is in the way here. I'm going to move it. Zoom thing. They're too small to properly represent and state their climate models. You can see here again, this is 100 kilometers. So these are really, 10 kilometer scale waves, right? So even if you have a really powerful GCM at 20 kilometers, which is really state of the art, or 50 kilometers more, still state of the art for CMIP, for climate modeling, there's no chance of getting these waves. Even if your nominal resolution gets down to on the order of 10 kilometers, you're not really resolving a wave at that point, right? So they're missing. So we have to parameterize them. And this is a very old problem. Sorry. So the first work on this was done by Tim Palmer in the 1980s. Looking where they had these systematically westerly biases. The story goes is in the 70s, the first general circulation models had a pretty reasonable representation of the jet streams. And then as you got better computers in the 1980s, what happened was the simulations got worse. And that's because as you start to resolve the synoptic variability, the storm scales better, there was in the beginning, there were some biases, canceling errors. And what happens is now missing these gravity waves meant that your circulation got quite biased. And it's a beautiful paper where they both diagnose the problem. They have some observations that we think there's a drag, move it forward. So you might ask, why, and if this has been 1985, why are we still worrying about this problem? It's probably because it's a really challenging problem, and Tim is really advocating that we should go down to 1 kilometer scale models. Maybe at that point you could get rid of the orographic gravity waves. But what we're finding is even then, a lot of the smaller scale waves, especially those generated by convection, the source of the waves itself depends on very small scales. And kilometer scale convection is not there yet. So I think it's still a problem there. And even to drive that home, tomorrow at 11 a.m. UTC, so that's 7 a.m. in New York, just getting it right, there's going to be a talk by Michael McIntyre on the missing gravity wave forces. So really smart people are still thinking about this. I think he's got more dynamical ideas on that. We're going to be using data to go after this, but it's still a vexing problem in the field. It's challenging. Why are we still at it 30 years later? We have limited observational constraints. As part of the data wave, we have these balloon observations, balloons that are going around 70 hectopascals. So we get a sense of what waves are going up into the stratosphere, which is important. But even then, we're going to have to use high resolution models to find out where they're breaking and what's going on. And I think it's a fair statement to say that often, the uncertainty is about an order of magnitude. I'll give some examples. You could really change things by a factor of 10, and that's still within the realm of observations. The other thing I think why it's still here is that there's the computational limitations that are faced by all parameterizations. There are very good parameterizations out there. For example, Ulrich Achatz and his group have MMSGWAM. It's a ray tracing. You're doing better physics, but it gets expensive. For applications where you really care about gravity waves, we may be willing to pay that. But for most climate modeling applications, no, it has to be sort of in the background, a few percent of CPU time or GPU time. So we're kind of hamstrung here. And that's why we thought, well, maybe a data-driven approach would give us some flexibility. So today we're going to be focusing on the QBO as sort of a test problem or quasi-binary oscillation. Though I want to emphasize that the real important things are really just the large-scale jet structure. If we could get that right, I think many people will be happy. These are not observations. These are 3 different model simulations in the QBOI initiative, where people have been looking at state-of-the-art models and their representation of the QBO. These are just tropical, zonal mean, zonal wind. So you're looking at jets in the tropics. And you get this alternation pattern of easterlies and westerlies that propagate, start up in just below the stratopause and then work down the way towards the tropopause. And it alternates every 28 months. It's my understanding that the first observations of the tropical stratosphere, they found one jet and they're like, okay, it must be, there's easterlies up there. They came back a year later. Oh, it was different. And it took a while to sort this out. These are, again, 3 models. This is not the real world, but they're all pretty close. You can say that in particular, they've been tuned to get this 28-month period. But there's some challenges. What we really want to do is get the QBO in the lower levels right, partly because that's where the QBO would interact with the troposphere. So if you want to get extra predictability out of it, we need to get that. And the models really struggle in their representation of the QBO lower down. Well, the QBOI initiative was interested in, okay, well, everybody gets the climatology about right. What happens if you move into a warmer world? What will happen to the QBO, and how might that affect predictability? Well, if you look at the community Earth system model, the high top version, the QBO speeds up. It becomes a quasi-annual oscillation under a warmer world. And here, when you're in an AMIP, these are atmospheric only models. How do you hack climate change? You increase your SSTs by 4K, like a 2K climate sensitivity, and then quadruple CO2. And combining that gives you a pretty fair representation of what would global warming. And what you find, again, this model predicts a quasi-annual oscillation. The ECM5SH, this is a German model. This is the precursor to the current Max Planck model, the ICON model. In this one, you actually lose the QBO in a warmer climate. Again, if we're at 4 Kelvin warmer, we're going to be worried about other things, but we would lose this oscillation. If you ask EMAC, this is another, the E here stands for ECM. So again, it's a model based on the Max Planck MPI model with messy atmospheric chemistry. So it's one that was built to do chemistry climate modeling. What happens in it is you get a slowdown of the QBO to become a quasi-triennial oscillation. And the verdict of this study by Jadvig was really, we don't know what's going to happen in the future, right? These are all credible models. We've tuned them to be right in the current climate. And they looked really carefully trying to figure out, could we differentiate why some models speed up and other ones slow down? And there's no clear cut, that, if you parameterize it this way, this happens. And we found ourselves that we can play with the same model, tweak the existing physics parameterization, and get both effects. That's why we were kind of going after this. We want to develop data-driven parameterizations of on and under resolved gravity waves. That under part is we're in the gray zone where the models are partially doing it. They're primitive equation or non-hydrostatic. They can make gravity waves, they're just not doing it well. And so we have to figure out what they're doing wrong and then add what's missing. And we want 2 main things. We want to capture or at least respect the physics. By that, in terms of a data-driven approach, we want good generalization, right? So if I train on certain training data, and then I go into online where I'm now going to be getting things from that same distribution, but new data, do I do a good job? And we'd like to be able to extrapolate. Now, I know that's a dangerous thing to do. We want to minimize extrapolation, but if you want to ask questions about like a QBO in a changing world, we are going to have to go away from today's distribution, right? So that, and we think that in physics is what allows you to extrapolate, right? So if we can incorporate physical knowledge, we have a better chance of doing that. We also want these things to be useful, right? For climate prediction, seasonal weather prediction. And that means these schemes you have to be able to calibrate them fairly quickly, right? You're going to put a bias model that's not perfect, You want to put your parameterization in, and it has to do the right thing without too much work. If it takes a graduate student 6 months to make it work, I don't think these things are going to be adopted well. And that's what we're going to focus a bit more on today, is this calibration problem. But I'll show that the extrapolation and calibration problems are sort of two sides of the same coin. So what makes this hard? The first problem is we're not, what we're aiming for is challenging, right? The gravity waves and their sources are unevenly resolved by models, right? So again, the models can get gravity waves, but it's really a function of what's the resolution, what are their numerics, which affects the effective resolution, and other possible biases. You can flip this and saying, well, part of this I have to learn what the model is doing wrong, or I can say when I have a high resolution data set, what am I trying to extract? And there's really two issues that come up. One I call sort of a method uncertainty is that you can say what effects of gravity waves need to be parameterized, right? There's many effects. Some of them are important, some are not. And there's a lot of nice work. This is Chong has a nice paper that's out in 2023 where they were looking at high resolution simulations with WRF, the Weather and Research Forecast Model. And then there's different ways of extracting gravity wave information, and they give you different answers. So which one do we want to use? And then the second issue, I'd say that's less related to methods, but it's just a sense of scales. So what scales are missing in the climate model I'm trying to predict, right? And we're current work with global models that are run at like ICON and IFS, for example. We find, if you say, well, it's 200 scale or 700 kilometer scale waves, you get very different answers. So we're working on those two challenges. The second thing, and this might be more unique to gravity waves, is that the sources themselves are a big source of uncertainty. So what produces the gravity wave? So mountains, we know where the mountains are, but what's your effective resolution of the mountain? But there's a lot of gravity waves, particularly in the tropics, that are generated by convection. Convection itself is generally parameterized. So it's one parameterization feeding another one, sort of a blind leading the blind situation. Frontogenesis is another source in the mid-latitudes. There we're more optimistic that these higher resolution simulations are going to start getting down to that frontal scale, right? But the convective problem is going to be around with us for some time. And just to give a sense of how uncertain it is and how people do this in the field right now, this is an example for the MERA reanalysis. So if you look at the first generation MERA, modern era retrospective reanalysis, they used a model. It's whenever you do reanalysis, you have an atmospheric model, right, that you assimilate data into. The background gravity wave parameterization for non-orographic or convective waves just had this flat in the tropics and then increased in the high latitudes, and that was to get fronts. And then what they did is when they went to from MERA to MERA 2, you were shifting from they wanted a model that would generate its own QBO, and it's fairly well known in the community that if you have more gravity wave driving, that helps a model that's missing some of the small scales to get a while. So they just arbitrarily ramped up the stress of the gravity by a factor of 8. Okay, and that's acceptable within our field right now because again, we don't have a good constraint on this. But this is the kind of thing. Well, if your model is missing convection, we'll just ramp it up. This is what we're up against. Okay, so all this means that the perfect parameterization is not going to work when you put it into a model, right? An imperfect model. I like to think of us as a very dated reference, but A Few Good Men, where the young Tom Cruise, idealistic. We're going to come in with a great parameterization. It's the truth, it's right, and then we're going to meet the grizzled climate modelers, and then ask them for the truth, and then you can't handle the truth. I went with my group, and no one had actually seen the movie, but I think there's a meme that people know, so it still carries over. So again, traditionally, how do we do this? Or, operationally, most parameterizations have tunable parameters, right? And with a physics parameterization, they have physical meaning. Your amplitude, which I showed you in the last slide, the spectral width gives us some insights, or the intermittency. These are physical knobs that we can tune. But now we're moving to a data-driven approach. Okay, now we have lots of parameters that have really no physical meaning, right? Nodes in a neural net, we can't say, oh, this means the amplitude. So how are we going to handle that? And again, we want something that, ultimately it needs to be a very straightforward procedure model, and they can, tune it with some work, but not, again, 6 months to make it work. The other challenge is, what do we mean by make it work? And I think that the problem here we're against, and this is probably other parameterizations are facing this as well, other parameterization fields, is that, people don't really care about what you're doing, right? People do care about gravity waves, but that's not essential, right? If I want to do climate prediction or a seasonal forecast, getting the gravity waves right is not as important. What I need to get right is the forecast, or I need to get my climate right? So there's a mismatch. When I'm training a parameterization, I'm looking at the process level, right? I'm building a function. This is my neural net random forest, whatever you're doing. You give me the model state, and I want to minimize the distance between that, its prediction, and the actual gravity wave tendency, the missing tendency. Here I've L2 norm, could be something else. But anyway, when we're training a data-driven parameterization, we're aiming at that. Like, get the gravity waves, get the missing gravity waves correct. But that's not really what people want. Right? People want is a good simulation. They want the emergent behavior. And that emergent behavior, for example, here we've been focusing on the QBO. They want the period of the QBO, which you need to run the model for a long time, right? To get a QBO, to get a period of something that takes 28 months. That's what they want. That's the objective function they're aiming for. There's a mismatch, right? And we might do a good job at getting the gravity waves, but not do a good job in getting the emergent behavior because there's other biases there. And that's what we're struggling with is how much do we fix other model biases versus stay true to the data and get the gravity waves. Okay, so what we thought with all this zoo of issues, what we do is we really simplify things greatly. So we're going to simplify our GCM, simplify the truth of the physics, and then now we can really start asking questions about data-driven methods. So we went back really to the founding of how we understand the QBO to a one-dimensional model. A theory, you can say, what is a theory? It's a system of equations. It's a model that explains something. The original work was done by Dick Linzen and Jim Holton. We ended up coalescing to a version of it that shaked out in about 10 years later, still before I was born. So this is old science, but still good science, with just two waves interacting with the mean flow. And here it's the whole equation. So that's the beauty of this. This is your GCM right now. Okay, it's just one-dimensional. So U, the zonal wind, is a function of height. The tendency, right, that we're trying to predict. You have advection. In the tropics, you have upwelling that tends to lift any anomaly upwards. And you have dissipation. Again, this is not molecular dissipation. This is other waves that are not in this 1D model. They will be taking away momentum and distributing it in the vertical and in the horizontal. It turns out is important. Okay, so that's our whole climate model. And then this is our parameterization of the gravity waves. And it boils down to it's an exponential of something minus, right? So if this thing here gets big, it's a saturation condition, then the gravity waves are going to break out. And the key feature that we're going to focus on here is this critical lines, that when a gravity wave's phase speed approaches that of the flow, then its vertical motion stops or slows down, so it'll have chance to be damping, and you also expect nonlinear braking. So the phase speed is very important for where a gravity wave is going to break, and then its amplitude will tell you how much momentum you get out of this. Okay, so those are the two parameters we're going to be playing with. In Ofer's model, what he did is he said, well, let's have a spectrum of waves here. The sum will be over a Gaussian packet. I think in some of Hamid's work, we can get it down to just two waves too, and you get the essential the same physics. The reason we did a whole packet is we wanted to think about, well, what happens is you vary the spectral width, the CW, like sort of how fast are these gravity waves, and that's really related to the depth of convection. Deeper convection will produce a wider spectrum. And then the amplitude, right? This FS naught just rescales all the amplitudes. And that roughly scales with the square of the precipitation, because we're looking at a quadratic quantity here. So we set the model up, we tune it to get a realistic climate. So you have the right period. We were also interested in amplitudes. I'm not going to talk about it here as much, but again, we want the amplitude of the QBO to be correct as well. And this will be our truth now. And what we want to do. And then what we want to do is figure, and I just wanted to explain a little bit how it works. This is your flow. This gravity wave term, what happens is that the critical line breaking is what stops waves. So when you have a shear zone here, westerly, all the westerly waves, C, which is positive, U minus C goes to 0. They break right here, and you deposit all that momentum in the shear zone that's going to pull this jet down. The easterly waves, they go on fine, they're happy until they get to this easterly shear zone, right? And all of a sudden they start to break. And again, it's in the shear zone, and it pulls this thing down. Here's the opposite phase. We had introduced some variability in our model, but this is the essential dynamics, the theory of the QBO. So we were interested in, Ofer Shamir, who the first author on this work, is can you train a scheme on the today's climate, and then how can you capture the response to QBO to changes in the parameters, focusing on the amplitude and spectral width. And then the flip of that is calibration. Okay, so if I have a train on the true model, now I'll give you a bias model where some of the parameters are wrong. To represent problems in a complete model. How do I fix it? And I'll give an example of both because it turns out they're so related. So first is, what do you do, right? You have a control integration. You have your inputs, your features. So this is the zonal wind. And every time you have, these are stochastic variables that are mimicking that of convection. What's your total amplitude and the spectral width? right? Okay, you get those. And then you get your outputs or your labels, what you're trying to predict. And you just have to, and you can see it really is focused in the shear zones because that's where most of these, most waves are hitting their critical lines. And you just have to learn that relationship. And we tried many different data-driven methods to go at this. Today, I'll only talk about a neural net, just a deep neural net. But the idea is you can test, we have our true model. This is the distribution of those inputs. It's just a PDF, right? And at any given time, you're getting a random sample corresponding to a sample of convection around the whole tropics. And that's why it's Gaussian, because we're imagining this is the whole tropical belt, all the waves being produced up there. So this is our control climate. You learn, let's go to the online. Can you generalize? Well, if you give me the same distributions of my input parameters, how well do we do? So this is the truth. Again, how well can we do it? When we found our emulators, and this is a neural net, but we found many emulators from random forest. If you do a boosting, worked quite well. We also looked at support vector regression. There were many ways to get a pretty decent, generalization within the same climatology. But then the question became, well, what happens, if you have a climate shift, right? Here, it's a contrived example, but you can imagine going from today's climate to a climate where you just have a systematic shift of this distribution to lower values. If you look here, you could say it's a reduction of the convective mass flux, could cause weaker gravity waves in the future. Not meant to be a realistic perturbation, but it's a perturbation. What happens is if you reduce the flux of momentum up into the atmosphere, the QBO slows down, right? It also becomes a little stronger. There's reasons for that. But the main idea you can think of is, well, we're just having less momentum in the shear zone. So that shear zone is always being advected upwards. If I have less of a torque, it takes longer to get down. Okay. So the question is, if I train over here with my emulator, what happens when I couple to the simulation with a bias? Okay. And what we found was, well, marginal. We got qualitatively right. The QBO slows down, but we have pushed our distribution quite far. Like we're getting now a lot of fluxes that were hardly ever seen in the control climate. And the neural net is struggling to extrapolate all the way to that. So you could say it's qualitatively right, but not all the way there. But possible. Why is this an issue? Because we can now flip this whole problem around and think about calibration. Okay. When I do calibration, it's going to be the exact same simulations, but just backwards. So I'm going to say, well, again, the truth is the control climate. Okay. But now I have a climate model. Okay. And my climate model has its own convective parameterization, and it's a biased parameterization. What they did is you have to make tough choices often in parameterizations. You can get the mean state right, or you can get the variability right. Often you have to get the mean state right. If your tropical warm pool convection isn't right, your whole climate is off. So imagine a climate model again. We can just say that the true world has deeper, stronger convection relative to this climate model. Okay, well, if I have my good data-driven parameterization over here, exact same simulation I'm showing you, but you can say this is what would happen if you just plug it into the bias model. Right? It's the parameterization is doing the right thing. It's saying, oh, you have the wrong climate forcing, then I'll give you a different gravity wave drag, right? It's doing the right thing, not perfectly as I showed you before, but now you'd have a biased QBO. It's 37 months. No one's going to use this in a climate, in a comparison project. It's classic garbage in, garbage out, right? We gave the parameterization the wrong inputs, it gave me the wrong outputs. So how can we fix this? And Ofer said this is sort of a first stab at it. You can say, well, in this case, it was just a problem between the distribution. Here's a cumulative distribution function of the model versus the truth. And what you can do is you can just remap. This is akin to traditional parameterization. You say, well, if I have a 30th percentile gravity wave flux in the model, well, I know that that's just systematically off, and I can remap it. This is a simple one where it's just a translation. You can do this in multiple dimensions and just remap the distributions to get the right. So you're saying whatever you give me model convection, I will convert that to real convection. And when you do that, you get back to something respectable in the control climate. Now, whether this would be good for extrapolation is another story, because you have to hope that the change in the model and the truth has that same bias as you go through it. Anyway, this was a simple one that was kind of like what we do with traditional parameterizations. It's saying, don't mess with the data-driven parameterization. Let's fix the inputs. But now we've been thinking about other problems that are probably more realistic. One is if you have other model biases that are not simply, oh, it's got the wrong convection. Here what we're showing is some simulations where you change the diffusivity, the kappa. We're thinking of that as a proxy for, okay, you have some biased model numerics, or you have some biases in your large-scale circulation. So your resolve waves aren't getting up there. They're not taking the momentum away. Again, we have the luxury of a true simulation, right? Because it's so simple. If you reduce the diffusivity, what you find is the QBO slows down, you get longer phases, and it gets stronger in amplitude. Or if you increase the diffusivity, basically because you're diffusing these shear zones down, you actually speed up the QBO a bit. So you get a faster 23 months versus 39 months. Okay. So now again, the problem is, well, what happens if I now bring in my neural net? Okay, it's an emulator. I have the control climate. I've trained it. I've done a good job. We've passed the data. We've generalized well to the right distribution. But now I plug it into this biased model that's got the wrong version of kappa, right? And as we saw before, we get qualitatively right behavior. The QBO slows down or speeds up. The quantitative is not quite right. It doesn't quite do it enough. So it's failed to fully extrapolate, but it's doing a pretty good job. But now the question is, what would you do if this was a real climate model simulation? First, you wouldn't know the physical result, right? All you would see is that, oh, I trained my model. It was good on the training. I put it into the climate model and it looks bad now, right? And again, in this simple context, we know it's getting the macroscopic behavior wrong for the right reasons. Your model has the wrong diffusivity. I'm actually parameterizing gravity waves pretty well. I'm doing a good job, but I'm not going to get that emergent behavior I want. And people aren't going to use the parameterization. So the question is, how do you calibrate it to make this palatable, right? I want to, basically, I need to have the right QBO, or I need to have the right jet stream. And I'm still have to change the data-driven parameterization, but we don't want to throw the baby out with the bathwater. I don't want to take away all the data constraints that we did to build this. Okay, so that's what we're kind of facing, and I think this is common to many parameterization problems. I'm going to stop here. I've left with a very difficult question, and we're not going to answer that today. But Hamid's looking at some more advanced ways to calibrate with online offline learning. I'm going to shut up and let him talk. But we're aiming towards this. Is how do you again calibrate without losing your data? And I'll stop there. No, let me stop sharing. Sorry.
Okay, yeah, thank you, Ed. It was great. It was fast. So I'm going to share my screen and continue the discussion. Should we wait for some questions, or should I go for the presentation and at the end? So,
yeah, let's do all the questions at the end, if that's okay.
Oh, okay. So let's share my desktop and then. Okay, great. Hopefully you're seeing my screen. Okay, so great. Yes, thanks for the opportunity. I'm Hamid Pahlavan. I'm a postdoc and part of the Datawave project, working with Pedram and John. So yeah, I'm going to continue the discussion on the training of neural network for parameterizations. And at first, I'm gonna talk about like learning strategies, in particular offline, online learning, and then I'm going to talk briefly about the importance of learning non-local dynamics for a stable and accurate data-driven parameterization. So let's consider a dynamical model, for example, a GCM with a data-driven parameterization D, where we want to learn the parameters theta, which can be the weights or biases of a neural network. So the most common approach is offline or supervised learning, where these parameters are learned using a gradient descent and finding a map between the resolved processes and the subgrid scale term. And offline learning is usually straightforward to implement, but it usually needs a large training data set that includes the subgrid scale term itself, which are usually hard to obtain. And also, when coupling it back to the model, to the dynamical model, it can lead to instabilities, as Ed mentioned. On the other hand, learning can be approached as an online task, which allows learning from time or space average statistics. For example, the period of the QBO. And as you can see, it doesn't need to have the subgrid scale term, so it is kind of data efficient. But online learning or online training a neural network can be difficult due to instabilities during the training. And also learning from statistics usually means long-term simulations during the training, which can be very challenging and expensive. So here we want to further explore these different learning strategies. And to do that, we also use the 1D model the 1D QBO model, which Ed did a great job in introducing it, so I'm not going to repeat it again. And actually, we are using the same code that is developed by Ed's group, by Ofer Shamir and et al. Probably the only difference here with the model that Ed showed is that our gravity wave forcing is deterministic here, and then the stochasticity in the model is coming from this randomly generated stochastic forcing. But we run this model and we get an oscillation which we call the true QBO, and it has a period and amplitude close to the observed QBO. And then we use a 12-layer convolutional neural network, which has around 12,000 parameters to learn the forcing term G. So the CNN gets profile of U and gives profiles of forcing G. And we also use two different data regimes. So one of them is a big data regime, which includes 100 years of data, denoted as CNN-BD. And the other one is a small data regime, which only has 18 consecutive months of data. And so it is a more realistic scenario considering the cost of gravity wave resolving simulations. And it is denoted as CNN-ST. We start by evaluating a priori or offline performance of the CNN trained in the big data regime. And this is a PDF comparing its its probability density function to that of the truth. And so you can see it has a great offline performance with our of the PDF.
Yeah.
And so when we couple this back to the 1D model and replace the physics-based parameterization, so it gives us this QBO, which has the same structure and period and amplitude as the true QBO. So it works perfectly. But if we go to the small data regime, which again is a more realistic scenario, then we can see that actually the offline performance decreases. The overall R squared is still high, it's still 0.9. But if you look at the PDF itself and also like the R squared at the tails of the PDF, we can see that it has clearly declined. Now, if we couple back this to the 1D model, now the oscillation is not stable or accurate anymore. And so here we can attribute in this unrealistic behavior to the insufficient training data set. But as Ed discussed, so this can happen to many different reasons during offline training. And so there are many challenges that is related to the, for example, complication of the extracting the true subgrid scale term from the high resolution simulations, or like the fundamental biases that exist between the base models and the target models, like high resolution models and GCMs, for example, due to biases in the sources of convection. So all of that can contribute to getting such an unrealistic behavior when we couple back our data-driven parameterization to a dynamical system. So regardless of what the reason is, so we are interested to see, can we use online learning to improve this data-driven parameterization and to rectify this unrealistic behavior? So for use ensemble Kalman inversion, which is a derivative-free optimization, and then it is ideal for GCMs. And we are using a package developed by Klima, also part of Wesri. And our setup includes 200 ensemble members and then 85 statistics, which include the QBO period and amplitude, for example. And our prior distributions are actually based on biases of the CNN trained in the small data regime. And so I should also mention that we find that we do not need to online retrain all of the layers of the CNN, and only online retraining the first and last data layer is enough to capture a stable QBO. And so here's the online performance of the CNN after online training. And so we are getting a QBO now that has a period structure and amplitude very close to the true QBO. We can also look at the PDF, for example, of the zonal mean to see how it's improved during the online training. So we have gone from this blue line, from CNN-SD, to this dash red line after online retraining. And so there's also some improvement in the PDF of the gravity wave drag, but it is not that significant. And I should mention that the performance of the EKI actually depends strongly on these choices of these hyperparameters. For example, we started by using only 2 statistics, including QBO period and amplitude, but system and the parameters are under constraint. So we were getting many different oscillations that were not realistic, including an upward propagating QBO. So we ended up adding actually cross correlation between several different levels, which turned out to be very important to capture the downward propagation of the QBO. Also, we were not able to online train a CNN from scratch, regardless of the number of ensemble or statistics that we are using. From scratch, meaning starting from random priors, and that shows the importance of priors during online learning. And here, because we start from the weight and biases from the CNN trained offline in a small data regime, we call this method and this approach offline-online learning, which actually start with an already offline trained neural network and then applies online learning upon it. But as actually, so there is a comment, okay. So one of the challenges actually that also Ed mentions is to make sure that we are getting the right answer for the right reason during the online training or the calibration. And so this is one thing that we are still working on it. But one idea that we thought about is to try to understand what the CNNs or what the neural networks are learning and how they are changing during this online retraining. And to do that, we use a spectral analysis of the kernels of the CNN. And so this approach is actually suggested by this paper. So we are following this paper, Adam Stubels from Pedram Group. And then I won't go through the details, but the main idea is that instead of looking at the kernels in a physical space, we can look at their Fourier transform. So here is a 5x5 kernel in a physical space. And so it's really hard to get any meaning out of this kernel. But if we apply Fourier transform to it, it actually turns out it is a low-pass filter. And so this is within a 2D turbulence, and so we can apply this approach to other kernels as well. And then what we get is a combination of low-pass, high-pass, and Gerber filters. And so this kind of insights can provide some meaning and how they are changing during the online retraining or calibration. So we use the same methodology. So we are using a 1D model. So our kernels are 1D. So when we apply the Fourier transform, we also get a combination of low pass, high pass, and band pass filters. And then half of the kernels are actually low pass and high pass filters, which are kind of consistent with the dynamics of the gravity wave propagation, which includes both local and non-local dynamics. But perhaps more interestingly is that the frequency of these kernels get closer to those in big data regime after online retraining. So for example, we are going from these blue lines in the CNN small data regime to these red dash lines after online retraining, which is closer to the black line based on the big data regime. And so this kind of analysis can provide some insight to the calibration process of the data-driven parameterizations. And so if you're interested to know more details about offline online training or these results, you can take a look at this paper, which actually came out a few months ago. And then I'm going to talk briefly about the importance of learning non-local dynamics for a stable and accurate parameterization. And so one of the challenges that we were encountering during this project was that we couldn't predict the online performance of a CNN based on offline metrics. So we usually hear this, that there's some misalignment between the offline metrics and online performance. And so it was very frustrating. So here I'm showing actually 2 CNN, which I simply call them CNN 1 and 2. And they have the same number of parameters and the same great offline performance, R squared of 0.99. But one of them is stable and the other one becomes unstable. So we wanted to really understand what is going on and what is being missed in the first CNN. And it turns out that we actually need 2 pieces of information, one from the dynamics of the QBO and the other one from the theory of machine learning. to explain this behavior. And so I start with the dynamics. And so you have seen in this gravity wave parameterization scheme in the one-dimensional, and I just want to emphasize the importance of non-local dynamics again. And then for a gravity wave parameterization to be stable, it needs to capture this non-locality. And this non-locality can also be seen in a correlation matrix between the zonal wind and the gravity wave drag. So for example, you can see that the gravity wave forcing at these higher levels is anti-correlated with the deep profile of U. And so this is the same the kind of non-locality that needs to be captured with the data-driven parameterization. And this non-locality actually is not something specific to the 1D model. If we look at, for example, we look at the observed QBO based on ERF5 reanalysis, we can see a very similar behavior. So that's one piece of the information. The other one is this concept of receptive field in a convolutional neural networks, and that's the size of the region in the input that produces one output. So for example, with the kernel size of 5, this output in the layer 1 can see these 5 levels in the input. And as we go deeper, the receptive field actually increases. And then for this output in the output layer, it actually can see 17 levels from the input. But it is important to note that it cannot see anywhere outside of the receptive field. So for example, if we change the zonal wind profile down here, it won't affect the output at the gravity wave drag at the 26 kilometer level. And we know this is not something that consistent with the dynamics. And then it turns out actually we can calculate the receptive field of a CNN using this equation, which makes intuitive sense. For example, you can increase the receptive field of a CNN by increasing the number of layers or adding a dilation or increasing the kernel size. So putting these two pieces of information together, we actually see that for a CNN to be stable, its receptive field has to be greater than the number of levels of the 1D model. In other words, it has to see the entire vertical profile of the zonal wind profile to be stable. So all of these models here have almost the same number of parameters, and they all have the same grade offline performance of 0.99, but they are different in their receptive field. And so as we increase the resolution of the 1D model and thereby increasing the number of levels of the 1D model, we need to increase the receptive field of a CNN either by increasing the number of layers or increasing the kernel size or increasing dilation to get a stable CNN. And actually, this is something also some sort of observation from this paper from Steve Hardiman and Adam Scaife from Met Office, that they also see like in an emulation of the gravity wave, they also see like a dilated CNN outperforms the other architectures. So this kind of results that we have here provide some explanations about that observation. Additionally, if we increase the resolution of a model for a fixed receptive field of a CNN, we can see actually the error also increases, especially at top of the model. But for the other architectures, for example, for a Fourier neural operator, which are non-local operators and are efficient in learning non-local dynamics, we can see that this is not the case. So this is actually something that we are working on and so drafting a manuscript, and I would be happy to chat more if you're interested. But to conclude, and going back to the problem that Ed brought up and I discussed a little bit, so we think, or at least I think, the online retraining is essential for incorporating any data-driven parameterization into the dynamical system due to all of the challenges and limitations that we discussed that happens during the offline training. And so this is probably the main and the key point here, but there are still some challenges. One of them is the computational cost of the online learning. And then there are some points here that we can discuss further. And the other point is what actually Ed brought up is that how to make sure that we are getting the right answer for the right reasons. And so with that, I stop here and thank you.